Get started. Welcome to Robotics 311. Whatever lecture this is, lecture 13. Couple announcements. Today we're going to review the planar model. This is going to be a big part of the last half of this course. So we're going to review that planar model, talk about the torque conversion. We're going to do a MATLAB exercise where you guys are going to build a torque conversion program in MATLAB from a skeleton that I've created. And hopefully we'll get the kinematic conversions after that. That's the plan for today. Few announcements. You guys hopefully saw my announcement about the IMU issue. Unless things have changed, the plan is to get your boards back. Then tomorrow during lab, we are going to go one by one to, there's a staff engineer. We're going to desolder the IMUs. They're going to take them, replace them with good ones, and resolder them and give them back. So we're going to have to desolder them with a soldering gun. We can do kind of group by group. We'll talk more about that tomorrow. Any questions on that? That came from so there's a really common and famous IMU, the ones that you guys are using actually, that was developed in California. And then that maker, Invensense, stopped producing the IMU. And I think they want people to start using their more advanced IMUs. So then places all around the world started creating this IMU and selling it, basically knockoffs of the ones that from Invensense. And so we needed a bunch of those IMUs, not only for this class, but for all sorts of stuff in robotics. We bought a bunch from a bunch of different suppliers. And one of the suppliers provided IMUs that are garbage. So now we don't really know, they all look the same. We don't really know which IMU sets are bad, so we're gonna replace them all. And then they'll go through later and test them one by one. So that's annoying, but it's kind of like living in the world of supply chain challenges and difficulty obtaining ICs. Cool, any questions about that? We'll talk more about tomorrow. Homework 3 was posted. It's due October 20th, class start. He's graded and posted grades for homework 1. He's gonna do homework 2 shortly, so you get those grades back. We'll post the solutions to homeworks and also the solutions to the quizzes that you guys have. And that's kind of in prep for the midterm that will be on November 8th. Cool? All right. Tomorrow's lab, we're going to begin kind of getting more familiar with coding using Python on your Raspberry Pi. So we're going to build from the image that you guys created and created the tools to log into. Now we're going to start developing Python programs. We're going to use Git, so you'll be working in your paired teams where you both can contribute to your code base using Git. So we'll kind of go through that, we'll set it up, go through it, forking, authentication, saving data. Then we'll do Python, looping and indexing, importing packages, which is a really big thing in Python and robotics. We're going to create a function, and that'll also go through saving data. So you'll be able to save data and then eventually view that data, which is important for creating robots. Eve.
Guys, if you have an image that doesn't work, or your Raspberry Pi image doesn't work, please try really hard to have that ready by Wednesday, because that's going to be an important part of the lab. I know you guys have previously forked the repos, and sometimes I know that was weird. If you're having that issue, I recommend just deleting that fork and then trying again, and that hopefully should fix the issue. If you're still having issues, we can definitely go work on that lab, but try really, really hard to make sure you have a working Raspberry Pi image.
Are there slides for going through how we did that in that initial lab? Or
Are posted.
okay.
Yeah. Everything that you guys have ever been given is essentially on Canvas. Except for business, which will be up there soon. But yeah, the lab slides are on Canvas.
Appreciate you.
Also, if you come, office hours is an easy time to go through that one-on-one. So if you guys come to my office hours or Eve's, we can do that rather quickly. So the image, how there's been an issue with the images, I cannot understand what's going on with that. So if anybody learns something that kind of tells them why that might have happened to a few people and not others, let us know. As far as I know, this image is really solid. So everything I know about this image and its setup indicates this should be a solid setup for you guys, and you guys shouldn't have problems, but yet some of you are having challenges. So help us understand that if you guys learn anything about it. Okay, that's lab 7. Now we're gonna get back to content. Okay, this is kind of where we are throughout the whole class. I keep showing this, but I think it's really important to kind of reorient you into what we're doing, because this project is deep. So I like to come back out of the depth for a little bit, and remind you guys where we are, and then we'll go back into the depth. So we've spec'd, that's kind of like step one, you guys have learned how to do that, choosing your different components, motor transmission ratio. We've done 3D modeling and manufacturing. That would typically happen after you kind of set up the layout of your robot. Because of the way we did the manufacturing in labs, we're going over kind of layout and geometry now. And normally that would happen after speccing, but we had already done that. So we gave you the information you needed to know through your sketches and your solid model files. This process of like understanding the layout and how systems are structured is very, very application specific. So we're doing a ton of depth on the ballbot, but that process would transfer to other projects, but obviously the exact mechanics would not. The overarching process would, so it's really specific to your application. So right now we're talking about moving torque and motion from one place to another, from a virtual coordinate system to the real coordinate system for helping with dynamics and control. Yeah. Okay. So we talked about the layout of our ballbot through several parameters. What was the deal? This is alpha. It kind of scaled a few things. What does alpha kind of govern loosely? Alpha is that angle. What does it trade or govern? It's sort of on the slide. Yeah.
Radial force, and it causes friction.
Yes. So as alpha is increased, we're going to have a larger force component here, which sort of makes sense. It's going to get larger and larger as we rotate the wheels around it. Its vertical component of force will always have to equal its mass times gravity. So we end up getting a lot more force as we rotate over. That force helps us because it helps prevent slipping, but it also hurts us because it creates more force on these omni wheels, which have friction and roll and slide. So we took a value of 45 degrees, which sort of balances these, and it's a common ballbot geometry. We picked our basketball radius. It's RK, it's about 120 millimeters, the radius of the ball. We picked omni wheels selected for you that have a radius of about 50 millimeters. So once we select alpha, all radius, and real radius, the system is essentially defined. There's one more piece of information that you would need before you could actually design everything. What is that last piece of information? Real radius, alpha, all radius, one other thing. Yeah.
It's like the distance that the wheel is like offset from the motor.
Yes, it's this distance here, the coupler distance. So like as you could imagine, we could sort of extend these motors, and we could lengthen that shaft arbitrarily. It wouldn't change the geometry of the system, it would just increase the center of mass height. So we specified that to be the smallest distance we could, the distance of that coupler, keep everything really low. We even have a cutout circle here so that the top of the base plate, whichever the ball doesn't interfere with the base plate, so it's sitting about as low as it can sit. So now everything is defined. Once you make those choices, there's nothing else to do but design your parts. So those are the choices we made originally for you. Yeah. That means that the wheels are actually contacting a circle around the top of the ball. Its radius is RK sine alpha. Okay, so this is kind of getting it closely at that, more looking at that coupler. So once we define these distances, like now you kind of know you could build this part. And you did. So once you've defined all these things, those parts could be built. It would give you that sketch that we gave you. There's also like a little bit of one dimension that's kind of specific to this setup. It has an eccentric motor shaft, so we need to account for that in its geometry as well. Okay, so that tells us the geometry, the decisions we had to make to get to that geometry, and this shows two versions that we made. First one, this was like June or something, and that we very quickly realized was not going to work. As you guys aptly pointed out before, it's flexing, so like you can tell these wheels are sitting way too low. That angle is no longer 45 degrees. And it was vibrating a lot because of the compliance. So this would not work. because we need the mechanics to be correct. So if we want alpha to be 45 degrees, it can't flex and be something different. Now then all the mechanics will be different. So we quickly realized that this was wrong or this wouldn't work, and we switched to more stiff mounts, which you guys noticed, and it also created pretty stiff mounts with the motors above the base plate. Okay. When we were doing our specking process, we originally talked about the planar model of the ballbot, reducing it to a single plane, and we did that to talk about rolling and get an understanding of how much torque would be required to roll that system. It was a little easier to model in one plane. In the actual control in the rest of the project, we're going to split the 3D system into 2 planes, and that'll let us analyze each plane separately and control around each plane without having to do the complex 3-dimensional mechanics. So that's where this is going. So we take our ball, project it into the XY or the YZ plane and the XZ plane, and it has a set of virtual wheels. Somebody tell me like where the virtual wheels are. They're sort of on that screen. One of them is, or 2 of them. Where are the virtual wheels? Yep.
It's on the XY, YZ, and ZX plane.
They would be, that's true. But specifically, they're in the XY plane, they're the origin. If it's not like leaning, they're the origin of the top of the ball, basically sitting on the top of the ball. And then the third wheel is on the x-axis, rotated at alpha degrees. And that's just how they've done that. The third wheel, which we see here, this wheel, doesn't actually come into play much if you're talking. We might actually change our control so where it maybe does come into play, but the first versions of control that we did this, it doesn't really come into play at all. Everything was about kind of leaning in the X, Z, and YZ planes and rolling in those planes. Can we think of like a different way of control if we wanted to use the XY plane? Can you guys tell what I'm saying when I say that the XY plane wasn't coming into the control or the mechanics? Because we're rolling it in these 2 planes, we don't care about what the sphere, so we don't really care about what direction it's heading. You're with me? Okay. Let's say there's another style of control, which would be like how we could command it. That might be easier. We're kind of debating switching to this. And we'll talk a lot more about it if we get there, but can anybody think about like is there a way to tell this thing what to do where that comes into play? This is like a kind of a difficult question, yeah.
Maybe we could try like spinning the thing that sits on top of the ball and then like drive it in a certain direction to use sort of like a polar form of control instead of Cartesian.
That is exactly right. And what might that do? Can you think of any advantages that might have?
Not sure.
It's okay, we'll come back to it. But what that would mean is, yeah, basically we're controlling in one plane, just like we modeled in the original specking process. And then we use sort of rotation around the other axis to control the other plane. So essentially it's putting it into a cylindrical coordinate system instead of Cartesian. That might be better. I'll talk more about why that would be better as we go through the lecture and start looking at the torque conversion. This was just to kind of refresh you on rolling physics. I think everybody was tracking that pretty well. Okay, this is still more into this 2 planes. I don't think there's necessarily anything I really need to say here that hasn't been said. Okay, so what we want to do now is talk about the conversion of torques. So if you're controlling the system or thinking about making it work, we're going to need to be able to understand the torques that are being applied in the planes, in the planar axes, and then convert those to the torques equivalent torques that would be applied in the actual motors, torques 1, 2, and 3. So that would be, let's say we're looking at one plane, we see that it's leaning, we want to correct that lean, we're going to send some torques, but we're going to send some torques to the motor, but we're going to understand those torques originally around the X and Y axes of this planar ballbot. So we need to know how to convert these. This is a big part of ballbots working well, is that this is done perfectly. So that's what we're going to talk about more today. We talked about aligning motor 1 to be along the y-axis. How many of you guys have opened the thesis or dissertation from ETH Zurich? All right, handful, good. So in that dissertation, we'll show some equations from it. All the math is described generally. So alpha and beta. Beta is this angle that rotates the torque of the motor 1 to be along the y-axis. So for that, we have chosen beta equal to 90 degrees. But if we look at that dissertation, you'll see there's beta in there. So that's what that is. And then alpha obviously is 45 degrees for our setup. Okay. Just out of like intuition, we have our x and y axes. We have our motor 1 torque, motor 2, motor 3. If I were to apply a torque around the x-axis, purely around the x-axis, which would send the ball this direction, what will those torques look like on torque 1 and torque 2, like qualitatively? Yeah.
I think you would have torque 1 is 0 and 2 and 3 would be doing something.
They were doing something. What would they be doing?
Equal work, equal
Yeah.
torque.
So they would be actually like providing mirrored forces. So that one force would be this way, one force would be that way, and if it's rolling straight along the y-axis, it's going to have equal torques, and they're going to oppose the torques that are kind of spreading it apart, and then the other two components will sum and it'll roll forwards. Good, okay, that's just a little intuition. Does everybody see how that's happening? Okay, that intuition I think will help. Okay, so we've rotated our coordinate system. The y-axis will be along motor 1. We've defined that there are 3 wheels, each spaced at 120 degrees. This is the kind of original setup. This is kind of saying that when we originally did the speccing, we sort of assumed maybe one motor. We could be providing all of this effort that was required, and the way we have it set up, one motor actually provides more effort than the other two. So that kind of aligned with our original speccing, which was on purpose. Could you have a ballbot with 4 wheels? 5 wheels? Yeah, you could. What that does is it would give you some other degrees of freedom. So there are 4-wheeled ballbots out there. We'll come back to that maybe. All right, so now I kind of want to talk you through this. I can't remember exactly where we landed on what slides, but I want to go through these step by step. And then in a few slides, you're going to make a MATLAB program that does all this. Okay, so what we want to do right now is understand the locations of these torques. We're converting torques from the XY plane to motor torques and vice versa. So what we want to do is understand, okay, where are these torques acting? Where are the contact points for the virtual wheels? Virtual wheels are sitting right here. What's the contact point? So we're going to say R WX. That's the contact point of the wheel in the X, that rotates along the X direction. It's going to be RK. And if it's straight up, it's going to be 0, 0, 1. So that says the moment arm from the ball center to the virtual wheel contact is straight up. And it's straight up to the radius of the ball. So that's how we know where the virtual wheels are located, on the top of the ball. What's our WY? What? The same thing. Yes, they both are sitting at the origin on the top of the ball. You guys know what the location for the other wheel is? It's like not shown in this picture. This is harder. It's gonna be 0, sine alpha, 0. So that says it's contacting along the x-axis, that's like right here. Contacting, it's along the x-axis. I mean, oh no, it's actually along the y-axis. So it's actually like here. Anyways. So this distance, RK sine alpha, is this circle. So it's saying our third virtual wheel that spins it around the z-axis is located on the same circle as the actual wheels. Okay, let's do the real contact points. What are the real contact points for these wheels? Where should they be? Yeah.
0 cosine alpha sine alpha.
Yes. Nice. Okay, RW2 is a little harder, so I'll give you that one. Same thing with RW3. Okay, so now we've defined our locations of our virtual wheels, our locations of our actual wheels, and they're kind of governed by this schematic here of our choosing locations of the virtual wheels. Yeah.
So is alpha the angle between like RK and like the vertical here in that description right there?
Alpha is this angle.
Right. So I guess I don't know. I was just looking at the trig involved. Like, wouldn't that align to the like to the within like the RK sine alpha here? Like, wouldn't that be RK cosine alpha? Because it's like the adjacent in that case if you draw a triangle.
This is a top-down view.
Yeah, no, I think it's
Oh, I'm
it's a
looking.
top-down view.
Okay.
It looks right.
Okay.
Yeah. Thanks for checking it. There definitely could always be an error, so please feel free to check stuff. Yeah.
I'm just trying to do for RW1. Why is it not just at 0, 1, 0? Like, because isn't it on the same spot? Like, isn't it just straight up on the TY? It's aligned with the y-axis. Isn't that how we oriented the axis? So I'm just kind of confused how the sine alpha, cosine alpha.
What is this? What is the distance of that circle?
It's RK. Oh, sine alpha.
Sine alpha.
Okay.
And then where's that cosine alpha come into play? Why does that say cosine alpha? Why do they all say cosine alpha?
That's the one with the z-axis.
That's the z-axis height difference. Yeah.
Okay. I was thinking that the entire wheel was RK, but I forgot sine alpha.
Yeah. Yep.
You probably went over this, but I think I missed it. Where did the root 3/2 and 1/2 come from?
It comes from the 120 degrees.
Oh, okay. Yeah.
I think you answered that last time. Last lecture. I
Yeah.
was like, where did this come from? And usually 120 degrees. Yes, that is right. It comes from the 120, it comes from around the 120 slash, also comes from beta. Beta is inside these parameters, these numbers here is also beta that we have extracted so that you don't have to see, we've defined beta and try to remove it as much as we could so it's not something you have to deal with. So they also come from that. All right, good. Okay, good questions. Now we're gonna talk about torques. So here's that circle. Here's our virtual wheel. Circle, circle. Actually, it could be an actual wheel. So now I want to talk through the forces. I'm going to define these. Oops. F, W, X be equal to okay, something about these forces. So the naming convention we're going to use for the forces, the subscript does not denote what axis that force is along. It denotes the component of torque that it creates, which changes its axis by 90 degrees. So this is FWX, but it's FWX acts along the y direction. That's just a convention kind of used in the math, but it has to be handled in some way. So same thing here, FWY. Why are we using, so RW, that's the wheel radius, yeah. Why are we using the wheel radius here? Well, people are thinking,
Well, I was just wondering, how does like the y force act along the x direction if it's at some angle?
FWX is going to be like right here. It's going to be right in the center, pointing that direction. And that's where the virtual wheel is rolling along, creating torque along the x direction. It would really be like this. Cool. So we're just defining these force vectors. The reason why we're using RW here is because this is the torque provided by these virtual wheels. So if we know that torque, we can determine its force by using the moment arm from the wheel. Yeah,
Is RW not the same as RK?
correct. Those are two different variables. RK is the ball radius, RW is the wheel radius.
Okay. Alright, gotcha.
Yes. Okay, so we have our virtual wheel forces. If we know our torques, we know our forces. That's pretty straightforward. Let's do our real forces. FW1. Here. These are kind of the same rationale. A little more, a little less clean vectors, but the same kind of rationale. If we know our torques, T1 through T3, we can determine those forces by using the radius of this wheel and then some geometry. Okay, so now we have our forces, virtual forces, real forces.
So when we're doing this conversion, are we like kind of assuming that the robot is sitting perfectly upright? Because otherwise the real wheel contact points would change according to that.
That's right, but that's true. When we actually do this, the coordinate system will move along with the ballbot. So it will end up being this, math will be the same. But in this analysis, everything is assumed to be totally vertical. This is just the geometry of it sitting perfectly vertical. How are the forces related to the torques? That's kind of what we've covered just now. We've defined the forces. Now we're going to define the torques.
Why was it -100 for FW1?
Because it's in this direction.
Oh, so it's applying a torque to the right, but it's really going to go to the left.
That's how it's drawn. Yeah, and this is sort of the convention that it's drawn with. We'll see how the sign convention comes into play in 1 second, actually. Okay. Now we have some information. We have some information about torques. We have some information about moment arms. And we want to put all that together and solve for torques. The way we're going to do that is we're going to say T1 plus T2 plus T3 has to equal Tx plus Ty plus Tz. So torque is conserved. The torque being applied by the wheels is going to be conserved as we move it from the real wheels to the virtual wheels. We want the torque to be conserved. What we maybe don't care about as much is the forces at those contact points, and we'll see that those change. Okay, so now what we want is RW1 cross FW1 plus RW2 cross FW2. Okay, so like we just defined these radiuses and those forces. So we actually convert those cross products and solve for torques. So I'm just gonna solve that for you. Okay. So if we use our equations we just defined, set our torques equal to each other, we can solve for T1 and T2 and T3 in terms of Tx and Ty, Tz. That's the answer. Yes.
On the bottom equation, is this supposed to be root 3 Tx or Ty?
Thanks. It should be Tx. Yep. Okay, so now we've just solved these. So now this set of equations will convert your x, y, z torques to 1, 2, 3 torques, to your motor torques. What does this mean? Or like, what does this seem interesting? And all the z component of torque just sort of comes out by itself in all the equations. Yeah.
It seems like for it to like rotate around the z-axis, all the wheels like contribute the same way by spinning it around.
Yes. Yes, that's right. So that might actually, we might exploit that. This is something we're thinking about right now in the control. So what I've done here is just paste the full equations from this dissertation. This is, so ETH Zurich dissertation, uploaded, that's the kind of reference. Here's our torque conversions solved for motor torques, the real torques, and our torque conversions solved for virtual torques. So what you see here is some betas in this expression. That's what it's a little uglier. So we removed the betas for you in all the expressions that we provided, but this is a general solution. And for us, beta is pi over 2, and alpha is pi over 4. So what I want you to do now, we're about to do this MATLAB exercise, which is I think gonna just drill this into you guys. This is a really important part of this creating a ballbot. So this is what I'm hoping you guys can create. This is called a quiver plot. Who's heard of a quiver plot? Okay, a quiver plot shows vectors. So you can give it receives an x, y vector, like a regular plot, but then also a UV vector that tells you magnitude and direction of a vector located at x, y. So what I've created here is a function where I define a tx and ty. That might come from our control in the future or something. So we define a tx and ty, and then we're going to convert that to motor torques 1, 2, and 3. Then you have to determine the contact point locations, which you just went over. And then I want you to plot them on a quiver plot. And if you do the math in the same sort of way that I do with the same variable naming convention, I left the quiver plot in there and it'll plot for you. But we'll get to that in a second. So what you're gonna do is induce a tx and ty, find the equivalent forces at their contact points, the real contact points, find the locations of the real contact points, and plot them on a quiver plot. I've done this for tx equals 3, ty equals 2, and then we're gonna reuse this function. So let me switch over to MATLAB and show you like what I have given you. I kind of want you guys to use this as an opportunity to really try to understand the geometry. It's going to come up a ton, and it has to be right or it will not work. Okay, so let me switch to laptops. Okay, so this is what I've given you. It's in files for lecture, lecture 13, torque conversion. So I've given you an M file that's mostly comments and blanks. So I want you guys to fill in those equations with if you use those variable names, it'll plot the quiver plot at the end. So you're going to define your tx and ty. That's going to be a couple of numbers. I give you 3 and 2. You can put those guys there. And I want you to find the virtual forces for the forces on the virtual wheels, fx and fy, the torques on the actual wheels, the wheel torques. Convert those torques to planar forces. Determine your planar contact points. This is a sanity check. So what this will do is take the tx and ty and recalculate them using t1 and t2 and make sure you get the same thing back from a different set of equations. So this t error should end up being 0. If that's 0, then your math is probably correct. Then the next thing is the quiver plotting. One quick thing about the way that I structured these, which just I thought was convenient. I made RW1, like a few of these things, I made them 1 by 2 vectors. So if you look, it says location of wheel 1, a 1 by 2 vector, that's in the XY plane. And then I structure those as a matrix and then use that for plotting. It just made it a little easier. So when you're done, you should have something that looks like this. I don't know what that 2 is doing. Should have something that looks like this. And if you run it, it should produce your quiver plot. What is the center arrow? What does the center arrow represent? Yeah.
Dx and ty.
And that is, this comes in TX and we're reviewing is the torques which just got converted by its radius of the wheel. Yeah, so that's TX and TY shown in force form. These are the torques on the wheels shown as their forces. And then each one of those vectors has a x component and a y component that's governing its direction. Okay. So this is kind of what I'm hoping to do for a little while. Is that you guys go through this. We'll use the lecture notes. Like I'm gonna leave this slide up. At least for now. If that's easiest. Okay. This so all the other ones, the other information, the contact points and everything else is provided earlier in the lecture. And if you go to Canvas lecture worksheets, download the lecture worksheet for today, it has all of that without my handwriting. It has all of it typed out. So it looks yeah.
So it's just zero, right?
Correct. In this example, and maybe like I don't know, the only reason the torque around the Z would ever come up is if we switch to this other way of control, the sort of cylindrical control. Otherwise, originally, yesterday I was thinking we would never talk about TZ, but now we might. Which one? Oh, TZ is 0.
Oh,
You might want to, oh, you guys can't see that. I probably should have included this like for clarity, but TZ should be 0. So I've added that now. So TZ is 0.
What is RK?
In actual numbers,
Yeah.
it's in your MATLAB script.
Oh. Thank you.
Yep. You guys get the line of sight to the solution relative to what you're doing. Does it make sense? What's where that comes from? That would make sense if this process would help make sense. It's actually writing that's what clear why we're doing it. You guys know what's going on? Any questions?
Yeah, so like when we were talking about it earlier, all the or vectors real, that's really big vectors, and it's just 3D. Like I'm kind of confused which,
They should still be, they can be 3D.
but you said that they're 1x2 vectors.
That's just because like the torque on the z-axis is 0.
Right, okay,
So everything will be in a plane.
oh, okay. Okay.
And also like we don't have a, I guess maybe there might be a quiver 3, but I don't know. Quiver is a 2D plot.
Okay.
So they like it had to be only a 2D.
Okay.
But there might be a quiver 2.
Gotcha.
Our concern is that I was wondering how it's gonna affect and why. Here. No, 1/2. Coming back and just do multiply that times. Oh, so it is supposed to be a vector, it's a vector, okay.
Yep.
So it is meant to be a vector, okay.
Yeah.
So after FXFY don't need to be vectors because they're only acting in one direction.
Right. And yeah, they actually are vectors, but they're other loaded to 0.
Yeah, okay.
So they're just two.
So it's gonna be 1/2.
When I hit run, I get an error saying that Viz Circles requires image processing toolbox.
Okay, just delete one of the circles. You guess you don't, so that's what plots those circles, like the ball circle and the contact circle, but you, I guess you don't have that.
Are we able to, oh, it's like opened up the add-on explorer, should we just like download the add-on?
Sure. Yeah, I don't know how I have it and you don't have it, but yeah, I think you should get it. We usually have access to everything in MATLAB.
It's column vectors?
If you're getting an error saying you don't have the toolbox for the viz circle command, it might walk you through the instructions to download that toolbox. You should have access to it. If you just comment out those or remove them, you just won't, it won't plot the circle, the contact circle and the ball circle. But the rest of it would still be correct.
What's your T error 0?
Sure.
Accidentally counted semicolon.
Are you guys doing
Calculate RW1 and RW2.
I left them as a 1/2. So I left it as a vector.
So you could,
If you look in the comment,
you could use
it's kind of like. That's what I did now. But don't only need that. So why consultants?
I have a question about effects in the function. Where do those go?
They come from your, so like in here somewhere, you're gonna have.
These ones?
Yeah, those are,
Okay,
so really should be a definition.
but then do I only use the top two? Or it's Z0, so it's just the same? Never mind.
Yep.
It was 7 too. I got the same thing.
Here's the same error.
You guys feel
Just
good about
downloading
the toolbox?
Yeah. I did all the equations. I have an error of 7 right now in my
Same.
torque
Okay.
thing. So
Yeah,
we
that's
go
what-
back and see.
7.33.
Same.
Uh-oh. Where are you getting your equations? Because like it is possible that in our like removal of the data term, that there's like a trigger somewhere.
Yeah, I did it
So did you use these equations or did you use ones from the notes?
in the notes.
Oh, okay. Okay, so there must be a trig issue in there. Could you try using these?
When it's downloading the thing and then I'll convert it.
Okay. I'll track that down. For now, use these. And then, so like after lecture, I'm gonna post my solution to this. So you have it. And then I'll track down if there's a trig error.
Oh,
Do your equations have beta in them?
it's fine.
So you're, I think, okay, so it's, I think, have you gotten all the way through it? I guess if people are using the equation of beta, that it'll work. And if there's a issue, it's my removal of beta.
The processing tool just takes a long time to download.
Are you using, how are you doing?
I don't know. I don't know what was.
We have a PT3 method. Super convenient for me since me and Pep's aren't too coming.
I'll be pretty active. I'm excited. Like I was like getting like studies kind of overwhelming at the beginning, just so many in a row. Wow, I'm pumped up.
Been out of early. Okay.
Cosine 90 is 0, right?
Yeah.
I think there's the equations in the notes, I'm fine with that, if there's a sign error or a trig error. Something's up, I think, because some people got the same answer that was wrong. My, in the notes, yeah,
I think I
Probably
used
in-
those equations.
it's like Canvas.
Why's my error 7, not 7.3333? Where's my integer?
I think I have something that looks similar, like not completely.
Yeah, no, I think that's right. Oh, wait,
I
okay.
did 2 3 things. Can you walk me through that?
Whatever is on the slides.
I think it's radius. That's not,
It's just RW, not RW.
that's not the RW one, no.
Oh.
I'm assuming it is, because that's the radius. Torque divided by radius.
Well, I guess.
And then that would be the direction.
It looks opposite.
But so,
It looks different from what it looks like.
There's such a lot of slides. Why is my yours?
I don't know.
so how did you do your?
It's at this angle. I didn't do anything.
Cosine's 90 terms should go to 0. So it's literally just gonna be the same.
Yeah, no, I use those quite. Oh wait, maybe that's why mine's 7 years. So
Are you adding like the cosine beta terms, or are you just ignoring them because they go to 0?
I had them there all the time.
I don't think I'm having the same issues.
You find it?
Beta just needs.
Yeah. So does yours work?
Well, mine gives me this, so I think this is really close.
I bet that's just like a syntax error.
Just one big cosine.
I would trust this.
It's similar.
Oh, I got 0. Yeah. I don't know, but I think it's the ones in lecture.
E1 minus root KTX. It's a plus sign here, it's a negative sign here. This one is here. One is right.
Yeah.
T2.
This one's right.
This should be positive.
Yeah. And 3 should also be positive.
For like, are you? I couldn't get. It doesn't visualize anything though.
All right.
Hit any
Measure
years.
on my dodger mistake.
0.
So if you use the equations from this slide, like they're fine. If you use the equations from this slide, those should be positive.
Oh yeah, that's probably why you.
What am I have my own problem.
No, I have the quiver error too.
But you don't.
Very impressive.
This is fixing it.
Yeah, I tried the other equation, so it only like 5.
You did with the whole beta and everything.
Yeah, I did with all the beta stuff, so maybe like that's the difference.
T1 though.
This one should be minus. No, the first one. Yeah, the first one should be minus.
Oh. Yeah, just like a divided by 2.
My hair is 9.7.
How do you think these coming up?
But I think this could be.
I mean, I don't even see the arrows.
I don't even see that circle. I was gonna do it.
Oh, no, that is it.
Yeah, why would you? Why would you? I mean, I'm gonna need some help. I ran it.
Yeah, there we go.
RS or WS.
TX goes
That sounds like.
Oh, because there's supposed to be 2 columns.
I think that is what it is.
Oh, maybe ours is supposed to be row vectors.
Is that what it is?
Even though they're written as columns.
It would be 2 vector.
It is very
Oh,
plausible.
or 3 by 0. 2 columns, 3 rows.
Okay.
And then, like if you, so you just want this to be.
Yeah.
Oh, yeah, so this one is just the position, so like,
Are we supposed to make the? I'm having like an indexing problem. So, is like when we have to determine like the axes, like these be column vectors or should they be row vectors?
I have them, like, it doesn't matter as long as they're in the way
But
that's
then it
written
makes,
here.
because then I think it makes, like if these are all columns,
They
then
should be rows.
when they get multiplied together, then it's just like one really long column vector.
They shouldn't be multiplied, they should be rows, and that just
Okay.
concatenates them.
Alright.
There's no vector multiplication in this.
But wouldn't it
Oh,
just,
that was not happening.
like this would just make one giant row as opposed to a matrix?
No, it should make a 2-column, 3-row matrix.
Oh, because I don't have.
For W1, should be a 1x2.
W, right?
I'm looking at the wrong thing, yeah.
W?
FW and yeah.
TX is 3, Y is
I'm still getting the error.
You just told us.
Oh, wait, it's a game.
No, you should also actually, you can include the large as your
It's going to leave the tolerances.
So that's not
That's
like
my
a
thing, is
What are the sizes?
I think it should be actually,
You see that this is,
Material field drilling.
No.
That, my graph breaks.
your betas.
Did yours work now? Huh, I'm getting the size of X must match the size of U for the number of column type.
1/3 times.
you don't need to include this equal component. This quiver is only, yeah, the
Did you
quad is
include
only.
betas in your T1, T2, and T3?
I'm doing dumb stuff.
I'm trying the one that doesn't have alpha.
What sort of toolbox this is?
I'm not gonna really do this all the time.
Some circle.
Oh, yeah. You need to do it for FX and F.
vectors, that looks maybe right. Who's thinks they're close? Alright, let's keep going. I'd love to move on to the next topic, but I don't know if we're gonna get there.
In the indexing problem. Wait, did you make your like, cause I'm having like, I'm having like a dimensions error. Like, did you make everything cause everything is column vectors, but
No, there should be.
then like these
Also be commas?
coming out is just, oh, it is a 3.
It should be just vectors of length 2 instead of 3.
Oh,
Because then when it
this E
concatenates
is,
with that.
yeah.
But yeah, we're just
So all of your vectors, the only like vector you create should be 2 row.
Yeah, I have
1x2s.
1x2, 1x2. And these are just the torques. 1x2s.
I'm curious as to why.
So where, when it gives you that horse cat error?
Yeah, I get why, like. But I want to know why.
Line 64, can you click?
But I guess.
So we wanna know like, so the size of the sizes are wrong. We can figure out, like, check and see them.
Yeah, because I mean they're printing out all here and they're all 1x2s.
But then they should be. So
I believe you changed to get rid of your 7.33. I am down. They were all negative and all positive.
Wait, sorry, was your RW like those 1x2s also, or did you
Yeah.
keep the third term?
It's 1x2. It shows on the right
Oh.
the shape.
Wait, I did that though, and now I'm saying like index in position 2 exceeds everything.
So if you notice what's going on there is that
Well, it's supposed to move, but it's not supposed to like, it's kind of glitching out.
our X1
It's very
locations, and then it provides locations for force at motor 1, motor 2, motor 3, and the orders.
Everything's wrong?
Everything should be a row vector.
Oh, because I thought when we like drew them out, they were all column vectors. So
Well, yeah.
oh, does it say?
Well, yeah, it all says
Oh,
1 by
1.
2, which
Okay, I was
means
thinking it the other way around. Shit, yeah. Right. My bad. Thank you.
Your error.
There's a coding issue.
Yeah, I can't. Well, here's the thing though. If I just take out this, like, because it's 0 anyway.
Cause like,
Oh, you're adding the sigma torque, and then it's not.
I'm pretty sure like it does like a
Yeah,
number
well,
The sigma
whatever.
point torque is not
Yeah, I was gonna
zero.
say, it really, it's not like, it's like running a game.
But my question is,
What
if
is
it's
running a
zero
zero? I mean like
anyways,
this one I think.
how come my
I don't
tier
even
is
know.
what's one?
I don't really fuck around
I
so
did
much.
Yeah, I put those things into how it's different.
Come on, no way, it still didn't work.
But like.
Oh, I think I know what.
I put TZ as
No, that's correct. The code, if you're saying it's zero and then it's showing you something that like something is.
Oh, shit.
If you add a non-zero to Z, the torques may not be.
Yeah. But I was just confused because I just put it in as zero. And it pops it up.
I think that's saying that there's the coding is in here, but I think it's.
Oh, yeah, that's true. That's like,
Force that we want to. What?
Yes.
Or no, we want to find T1, T2, T3, because that's maybe we want to apply more motors. Because at the end, we're ultimately find, do we want to know the forces and the torque?
Okay. Wow,
We want.
I mean,
When you say everything, what do you mean by everything?
I don't think we.
so is it like?
Everything is two-dimensional. RWS.
Okay, so this is my
So like, that's it, right? And then it's like reporting packages, which like you guys are doing.
Dimensions of array being concatenated or not.
Speed in the x direction, we can know.
I guess I don't know what the other two are.
This would be
Yeah, because our motors, the ultimate thing that we our motors output is the torque.
It's the torque that matters, yeah.
So why does the force in x and y direction matter?
Oh, you're not multiplying that by the.
I think it's just a means thing.
Oh. We don't get this. Yeah.
3 by 2.
You use the torque to find the force. Okay.
When I
Plus this, process vectors are just
Yeah, I think it's.
Like I think there's max lane.
What we're doing here is we write this down.
Because otherwise, I feel like this thing would just go forward because those are the torque speaking to that one.
Well, yeah, it's
The first two
something.
4 years.
The first movie, well, yeah, but like, I mean, they couldn't wait that long in between, like,
I guess they probably start shooting this out right after
I think so. I have one more question. Like, I don't know why like I literally tried that and so these are just these are row vectors of 2 dimensions each, which makes this a
much like 90% of its own just to get
oh sorry yeah
When I first started grad school,
makes that a 3 by 2.
I would do like.
a Libra actually animate character.
It's the same thing here. Each makes that a 3 by 2. I've gone back and forth between this being a column and a row, but neither of them worked, so like I'm not really sure.
Well, they should be.
Did you make that?
Fx and Fy should be scalars.
I can't.
Just put a zero.
There you go. Thank you.
So no interpret. Yeah, but a line of like it's longer than like.
Just change that to one and avoid
I was like,
That took way too long.
Who has the plots? All right. Do you guys think those plots are correct? Okay. Let's take there's still I think a few who don't have plots. I'm gonna go like 1 minute with them, try to get everybody on the same page. Then I'm just gonna kind of show you some of the vectors. We're gonna talk about them for a second, and we're gonna stop.
I don't know.
This is right. What if it's just moving in that direction? Yeah.
Cause it's moving up and that way,
Okay,
right?
yeah.
Just go down where it's
Moving.
Yeah.
Yeah.
That's what we use to transfer instructions at a particular frequency
Just moving.
I mean, we don't have homework, I was doing like the lab is the homework, but I've never
Oh, wait, yeah.
I've never not finished the lab class, I was big.
Oh, yeah.
Yeah, they can't,
That's also.
right, yeah, so this is right.
Yeah, this is fine.
Okay, cool.
Okay, if we apply a torque around the x-axis, it's gonna move in what direction? Around the x-axis, it's gonna move which way? Y. It's gonna move Y. So if this is right, I just gave it a big torque on the x-axis, the y-axis torque is 0. What should we see? You should see two torques and forces going away from each other that are antisymmetric. So this is the torques or forces on our two actual wheels. This blue force is the force that we're trying to infuse to our virtual wheels. And so now like that checks out, that makes sense.
Affects this T1.
So we know that we want to move along the y-axis. So we use all this in to get the force along each wheel. Is that what we will be outputting on the motor to move in that direction, or will we be using the torques?
Let's say, okay, the question is like, what are we gonna do with this information?
Yeah.
All right, so let's say this is your ballbot base plate. And let's say this is the x-axis.
Yeah.
And it starts to lean to fall over.
Okay.
You can measure that with, which we'll get to. You measure it with an IMU.
Yeah.
Then you can understand that it's falling and correct for it. So you know like, okay, I would need to apply a torque to put it back up.
Okay.
Like how do you take that concept and provide torque to the wheels?
So we know we want to, so if we start rotating this way, we know we want to rotate around the x-axis. So we can apply a torque on each of the motors according to that.
That generate a restorative torque around the x-axis.
Right.
So the x, like the planar model, the x and y axes, that's gonna be how we talk about the motion of the ballbot. When it leans, we're gonna talk about it leaning in that around the x-axis or around the y-axis. When we talk about like commands that are being sent and torque that's being sent, that's gonna go to motors 1, 2, and 3. So that's when all this is gonna come into play.
But if the motors are outputting torque, why does the force on each wheel matter?
It only matters if we wanna visualize it with quiver plot.
Okay.
Yeah, I mean, I didn't have a way to sanity check this without viewing the forces.
Right.
So that's why we did that. Yeah, just sort of check ourselves and make sure that everything's correct. Yeah,
For the forces on the virtual wheels, for the like f of x and f of y terms, why did you use t of y for f of x and t of x for f of y?
oh, good question. That's because of this idea that like the way that equations talk about this is that the force on the x, the force in the x, like with subscript x, is the force that creates a torque on the x-axis, not a force in the x-axis.
Okay.
So that's why those are off by 90 degrees. Yeah. So here's one more thing that we'll talk about for a minute. Remember I was saying like we could do this cylindrical motion? That might be better.
X and Y.
This is why I think that it's better. Let's say we only let the ballbot roll forwards on the y-axis. Now, no matter what, we're in a situation where the torques are provided by two motors and they're antisymmetric. And that seems one, simpler, two, more stable. As opposed to what we could do to say it can go anywhere in the plane. It can go along any direction in the XY plane. If we constrain it to going along the x-axis, it will have effort profiles that look like this. Then we can move it with the TZ torque. And then we would put it into something like cylindrical control. And that's just an idea that we just had, that maybe will be better. It's like, look what happens if we make this something different. Let's rotate this to be the other way. And I'll give it 1 Newton meter in the X. So like now it has, it's providing, the commands to the motors are very different, not symmetric. It sort of begins to do things that move in ways that are very difficult to intuit when it starts to go away from those axes because it's at 120 degrees and there's sliding components that exist at the omni wheel. So it's easy to imagine when it's moving about the y-axis. When it starts to provide torques around the other axes, it becomes difficult to intuit. Does that make sense? Okay, any questions on this? We're gonna stop here. I think you might use this program tomorrow, which would be kind of cool, program in Python, but we'll see. There are some other options. I will see you guys tomorrow. Come to office hours if you want.